So we've asked these four companies to join us today and give us a sense of, you know, obviously kind of where they see the industry going, but in the context of how they're working with, you know, their customers that are out there, you know, doing many of the things that we've been talking about at this conference. And I think the nice thing about this group is it's a good mix of, you know, different segments of the market. I don't think you're going to see much overlap. You know, we've got Martin Fornage here. He's the CTO and co-founder of Enphase Energy. So they're doing some really interesting things with advanced inverter technologies and power electronics for PV. Mike Edmonds, Vice President, Strategic Solutions with S&C Electric. So they're kind of coming at it from a, you know, they've you know, been in this industry a long time and have worked with, you know, probably most utilities out there, and really are kind of at the core of the distribution grid infrastructure with many of their products. Thomas Johnson, Head of Distribution Solutions for Itron. Itron obviously has a long history in this market, and obviously, you know, kind of started with metering technology, and then as AMI came out, you know, it became more of a communications company, and obviously, you know, are working with things like data and MDM. So they're kind of coming at it from that perspective. And then Vasilis Nikolopoulos is the CEO and co-founder of a company called Intolin. They're probably the newest, you know, smallest company here, but interesting startup. Originally founded in Greece, but I think now you're based in the US, in New York, yeah. And they're doing really interesting things kind of on the consumer side, and with some gamification technology, and trying to get you know, consumer engagement beefed up, and Vasilis will walk us through kind of that aspect of it. So what we're going to do is each of these gentlemen is going to have 15 minutes. We're going to try to really stick to that, to kind of run through a quick presentation, and then at the end we're going to save all the Q&A for them as a group at the end. So we'll have about 15 minutes or so at the end to you know, ask any of them specific questions. So Martin, feel free to get us started.
Thank you, Rick. I'm very happy to be here today. Okay, so we will talk about the DER and distribution grid and what it does to it. So what is the situation today? Well, solar penetration is growing very quickly indeed, and not only that, but it's not stopping. As we've seen yesterday again, you know, all consensus is that penetration is going to go even faster and further. At the same time, utilities are facing a perfect storm. Not only is there loss of revenue, but there are, because of net metering, but global warming is creating pressure to reduce coal-based power plants, and is also creating negative impact onto both the transmission system and the generation, because, well, temperature increases, efficiencies of the power plant is reduced, the losses on the transmission lines are increasing. There are threats for fire threats under the transmission line, create some outages. And there are some generation plants are even running out of water from time to time. So there all are subtle influences, but going in the wrong direction. On top of it, the emergence of solar is creating technical challenges. Now we see very much deeply changing power flows in the distribution network, which have impact on the voltage and frequency regulation. Additionally, I believe it's now technically feasible, if not always economical, to actually partially or fully disconnect from the grid operator. There was a statistic that showed that 16% of German companies now make their own electricity through CHP type systems. That's creating even further impact on the grid systems. And last, global unrest is creating terrorist threats or fostering terrorist threats, both on the physical level and on the cybersecurity point of view. And at the same time, utilities have limited options because they are governed by PUCs and legislation, have limited leeways in their actions. We also see that planning tools, especially in distribution system, are lacking or missing, as the gentleman from Duke said yesterday. And additionally, customers are resisting most changes. One has to look at the deployment of smart meter by PG&E a couple of years back to show that customers are not always too rational about their reaction. So what do we need to do? Well, we believe, Enphase believes that we'll do whatever it takes to increase solar penetration because it's good for everybody. It's the lowest incremental cost of energy, it's the lowest carbon footprint, it can be leveraged to help the grid operation as well. And what is very important is also helps, it actually creates a new mindset where end users actually become part of the grid. I think it's very important for the future. There is a host of technical solutions that are needed to increase DER penetration. So-called advanced grid functions, being able to write through faults of short duration, such as low voltage, high voltage, frequency. We need to put in the inverters or dynamic behaviors to affect power production with either voltage or frequency. We also need to be able to provide volt-var functions and fixed power factor type function. And we certainly believe that storage will have a huge role to play in mitigating the advance of solar. And also provide spinning reserves for utilities. Last, we can provide significant data to the operators to better operate that network and better know their network. And we'll get to that in a second. One thing which is important to see is that distributed technologies always win as long as they are managed. We have seen that in computers, I've seen that firsthand in telecom, transportation, it's true everywhere. And if one thing is true is that we have demonstrated that distributed power conversion on a given PV plant is something that was very feasible as long as it was managed, as we have proven. But I also believe that in a larger context, it's also necessary for DER to be managed in general. And I believe that today there is really no good path for DER management in the distribution system. Flow of information is very limited, and I believe that the AMI system lacks bandwidth and response time necessary to have dynamic behavior. And we'll have to rely on other means, such as public telecommunication systems, which create availability and security issues. Additionally, I believe that the standards are varied and not always convergent, and the contents of the message and the protocol are not quite there. I think we're short as far as the flexibility of the protocols that are on the table today. And last but not least, there is no clear division of functions. You have to look at the management of DER in a two-way approach. One is from the grid operator point of view, and one is from the end user point of view or the operator point of view of the PV plant. And the requirements are quite different. We have been, of course, very strong in management from the end user point of view, but this is no really good way to do management from the operator point of view today. So I believe a consequence of this is that we need a clear roadmap for DER management, especially on the operator point of view. Utilities should be able to know what capacity is available today at this second and what capacity is available in the next minute, 5 minutes, 10 minutes, hours. Utilities should be able to dispatch resources in case of storage. You definitely have the spinning reserve needs to be accessible. And I believe there should be a means to reward the usage of the utility of the DER advanced functions. And that's lacking today. Last, I believe that the PV inverters, for once, need to have real-time access to the meter data, which is not a feasibility at this point. I mean, it's actually feasible in technology way, but it's not done. A lot of the standard we have says that we have to do a given behavior based on the PCC voltage or frequency, but the truth is we don't have access to that data. It's actually buried in the meter. On the customer-facing point of view, well, we certainly have pioneered managed DER. We have 160,000 managed systems worldwide. We get over 500 gigabytes of data per day in our server. We have over 100 terabytes of data archived. There is a tremendous amount of knowledge that we have on operating condition of the network. We know, of course, about voltage and frequency, but we can also analyze distortions and so on and so forth. So a lot of operating conditions can be done, can be recovered. And this on a very small granularity time-wise. We can also change behavior remotely. We can upgrade inverters. We can change behavior. That has been proven very useful in many applications. In a special case, on the island of Kauai, we had Kiyuk was very worried about the trip points of the inverters because they were worried that the power plants all over the island the PV power plant will get off service when the frequency will go too low, such in case where there is a lack of energy going to the network. And if PV goes out at the worst time, that means that the whole island could possibly have serious problem of stability. So we, at their request, we actually change voltage and frequency trip points on all our systems overnight. And that proved out to be very effective for them in improving the stability of the network. Here's an interesting picture. On the left, you have the map of the island of Oahu. You see in dark blue the map of the feeders that are impacted by high penetration of solar. And in this case, the penetration of solar is looked at percentage of DG capacity versus the minimum load in the feeder. And we can see that this ratio is going over 100% in a lot of locations. And of course, HECO is very concerned about this because they don't have any means of controlling, they have very limited means rather to control voltage in these locations. And therefore, they have been curtailing solar deployment in those locations. And on the right, you can see that there is the map of all the Enphase systems in that same island. And you can see a very, very good correlation between impacted feeders and the data that we have. All these systems have real-time data on voltage, frequency, and more. So I believe we can leverage this database to actually figure out if we can increase solar in some location or what does need to happen to increase solar in these locations. This is a very, very powerful picture, and we can help operate the network better as long as we can exchange data with the utility. So what does need to change? Well, the first thing is that attitudes needed to change. I'm actually very happy about this conference because we can see that attitudes are changing and everybody's realizing that we are on the same boat or on the same planet. And I'm very happy with that. It's since last year I've seen a tremendous change on all sides actually on attitude. I believe that utility business model will need to adapt to changing environment. The way things have been done for a long, long time is probably not sufficient anymore or adequate. I believe we need to have adequate standards. The job of a PV inverter manufacturer is very difficult today because we see emergence of new requirements all over the place. Every country has a new requirement, every utility has a possible new requirement, every AHJ has a new requirement. It's very difficult to manage certification process, to manage the testing of all these different variations all over the place. And I'm really hopeful that we can get to a point where there will be standards that we'll be able to, we can certify to, that can allow plenty of movement for the utilities or the operators to change behavior, but in a given framework. I also believe that there are barriers to data exchange today between utilities and the end users. I cannot give all the end user data to the utility, and the utility cannot give us their feeder network data. I think we can work together. If we can work together, we can actually leverage a lot more of the information we have currently access to. Very importantly, I believe that network design and operation needs to change. We need to operate things in a much more dynamic manner than was ever true before. Inverter behavior should be able to change on an hourly basis based on expected conditions. And we are not there yet. As a matter of fact, we kind of prohibited from doing that. So there is a lot of work to do ahead of us to be able to operate all these DGs in a dynamic manner. And last but not least, I believe precisions about islanding need to change. I think that if we could actually operate a fraction of a network while the other is seeing an outage is a very good thing. And I believe that if we had the right technical solution with reclosures and so on and so forth, we could actually island pieces of the network with that and improving the robustness of it. concludes the presentation.
Thanks so much, Martin.
Thank you.
All right. Mike?
Thank you. Good morning, I think it still is, this side of the country. So I'm going to talk about two specific real examples of deploying technology to the grid edge. Luckily, David Wade didn't steal too much, but I will be talking about EPB shortly. Here, I just wanted to highlight where I'm talking about in the grid. There's integrated control rooms, substations, and I'm specifically going to talk about distributed intelligence. You heard Jason talk just before about some of the things that Duke have been doing, but I want to talk here specifically about how grid intelligence impacts distribution automation and some of the things that actually implies. And in this particular case, I wanted to be clear, there's no mothership involved. So in the case of distributed intelligence from my company's point of view, the devices talk to each other and they share information about real-time conditions of the system. They know the capacities that they have, both voltage and current and MVA, KVA, and so they know where there's spare capacity, they know where there's real-time voltage at each individual phase, and they're constantly sharing that information. So when something happens in the grid and they lose power, they already know where the capacity could be to actually reroute that power. And that goes without going to a centralized system to ask for a low flow, to ask for permission to open or close a particular area. And that's important for some of the architecture we've been talking about, is that it actually allows the ability to work when there is a communication failure back to the centralized system. But it's not an or. You don't use distributed intelligence or centralized. It's actually providing the two together is the key success that we've seen here. And one of those things is the speed of what the electrical grid needs to do. And what I mean by this is, I'm a power engineer by training many years ago, and I remember being told about something called protection and coordination. And we were told to set protection up and you leave it alone. And you leave it alone for maybe 10 years, and maybe you come back later on and check and see if it's okay. Well, today you can change protection settings in real time. So those things I was taught that you should never do as a protection and coordination part of my power engineering, you can now do. But to do that, you need to communicate in under 100 milliseconds. You need to be able to have a prioritized communication system, and you need to talk together. You don't go back to a centralized source to do a protection control settings to come back. So some of the speed and the facilities that you can do in the distribution grid, and I'm talking typically 69 kV and below, really requires the type of communications that communicate very quickly, have those priorities, and actually talk to each other very quickly. And in fact, David Wade didn't mention it, but I do know EPB are already deploying this type of technology. We call it communication enhanced coordination. So it's about how quickly you react in the grid. I thought the previous speaker made a very good point. I've just remembered, so you've helped me on this one. One of the things I've been frustrated to, and those of you know PTI and PSSE, that was actually what I used to do before I came to S&C. I've been really frustrated with planning tools. I've found that planning tools to help us look at the grid do not take into account this new technology. I had a conversation with an independent planning tool provider just 2 months ago about distributed intelligence. And I'd like to model that in the tool to actually see what power flows, low flows, dynamics would do. And the response I got back was, well, it's not here yet. You know, you just heard from EPB there's a huge deployment already. So I'm kind of frustrated that planning tools are actually behind the curve for some of this technology. And we did, I'll talk later on, we did a big study for Texas utility. And we ended up having to have a lot of changes done in the planning tool to be able to look at distributed storage and the impact of distributed storage from a planning perspective in the grid. Anyway, so thank you for listening to that one. Distribution automation. So this particular case, Chattanooga identified that they were actually inflicting $45 million worth of annual costs on their consumers. So as the consumers were suffering by having outages that cost them money. And if you haven't already seen it, I'd encourage you to look at a study or a book available from Lawrence Berkeley National Labs It was sponsored by the DOE back in 2005 and has been updated since. And that actually gives a very good estimate of the cost of the lack of power from both the consumer, commercial, industrial, agriculture, and the whole area. So you can work out from the consumer side the lack of power and those costs. And that's what Chattanooga did. So they said, with our current reliability indices, we're actually costing our consumers $45 million of lack of power. And they use that for their justification putting smart grid in. And the numbers, I should have updated those. I heard, David Way said this morning it's about 60%. So 55% reduction in outages, improvements in reliability, actually worked out to a savings for their consumers of $55 million a year. Why is that important? Well, it's attracted industries to that particular area where they have a very reliable system. And their consumers have been engaged. I've got some examples in a minute of that. But that's from the consumer side. From the actual utility side, this is a real storm event that happened in July of 2012, where you'll actually see there's red and blue dots here. So the red dots are the areas where they had an outage, and the blue dots are where they did not have an outage because they had smart grid. So you can start to see the penetration. By the way, the system wasn't fully deployed. But you can start to see the penetration of technology to avoid those outages within their particular operating area. More importantly, from the grid standpoint, the utility side, they actually got their grid up 36 hours earlier. Now, you remember overhead distribution, poles fall down. You don't have an automatic way of rehealing those just yet. So they have to go out and do some work. So that was actually 36 hours quicker to do. And they actually estimated they saved $1.4 million of their own utility costs. That's in addition to the consumer savings as well. So you start to measure some of those areas and get the payback for your particular investment. And we started looking at that particular incident. So there were 58 million customer minutes of interruptions saved by actually having this system actually rehealed within tens of seconds. The 77,000 homes would have been impacted before. 42,000 consumers and businesses were direct beneficiaries of it. 55% was restored to automation, and like I said, 58 million customer minutes of interruption were avoided. So that's a particular example of a grid edge application. Now those devices you saw have the ability to do the talking to each other. EPP does have a fiber network, so they actually can talk very quickly to each other and share that information, which is why they can also do the communication enhanced coordination. But that was an example here, and as you can tell, we're still getting a lot of data from this particular deployment of how they actually get the values of their system, and they use it very well. So from the single customer event, they actually very good at talking to the consumer. So this was a cut and paste, and I would encourage you to join EPP's Facebook page because you actually do get this live coming in. So I actually know on my Facebook when they've had an outage. But they really engage with the consumers, and here you can see a consumer on Facebook. Power flickers actually went out for a few seconds. It's totally different from the last time our power went out. I guess that smart grid thing you guys implemented does work. So it's that level of engagement from the consumer side of explaining that from there. And I think that's part of the things that we're starting to see change. Something that I encourage you to look for in the future, something called momentary outages. So we talked here about sustained outages. So a sustained outage is 1 minute or more of lack of power. Momentaries are literally that, a momentary outage, a couple of seconds. And you actually see those. So your clock at home will probably ride through it today. But I was actually checking out of a hotel in Florida about 3 months ago from a short vacation. And their systems went down because they had a momentary outage. The lights were on, the whole systems had to reboot. There's actually quite a cost to momentary outages, and we're starting to see some operators starting to concentrate on how you actually avoid momentary outages. So I think that's an important point for us in the future. And by the way, 5 minutes before you start recording an outage is archaic. There are countries around the world who actually demand that you start recording outages at 1 minute. So I'll give you an example. Illinois, we have a consumer-owned utility, a municipality whose average out Naperville has an average outage of about 20 minutes a year, compared to ComEd, the bigger utility in Illinois, her average outage is 2.5 hours. And that's not a high watermark. That's low. We need to start improving those. So thank you for listening. The other part I wanted to talk about was energy storage in terms of at the edge of the grid energy storage. I think I've heard through this conference multi-megawatts, which is typically substation based, and I would argue not at the edge of the actual grid. So we've been producing a unit which we actually call a community energy storage device. Had almost 100 in the field now operating, and we actually applied for this in the UK. So this is an area where a typical UK type house actually only takes 1.2 kilowatts as opposed to our hungry houses here of 4, 5, 6 kilowatts. So we actually put 3 devices there. There's actually a measurement, you can actually see some peak shaving here of actually using these devices, and they're single phase devices of deploying them for those particular low carbon network houses. We took a couple of important points away. For the size of storage, it's not going to fit on the sidewalk in Europe. So they really need to be on a utility property. Energy requirements are different. I just mentioned that just from a consumption standpoint. We also noticed that in this particular case, you think, and tell by my accent, I was originally from that island. It actually rains a lot. I actually don't miss that anymore. But it certainly rains a lot, and one of the things there was surprised me to see the amount of PV there. There was a lot of use of voltage smoothing, and that's been one of the key things we've learned about storage. Is as storage goes in the grid, you may think about it for energy use or power use. I can tell you, our grid edge devices are spending all their time doing voltage cleaning. Some sort of voltage type of injection to smooth the voltage, to get it to the right regulatory point, to counteract harmonics in the grid, to do something. So that's kind of one of the big learning things from that. And no surprise for a European application, we really need a 3-phase rather than a single-phase storage device, which is what we see here. And this leads me to my last slide. So 3 minutes, excellent. You may or may not have seen in the press that Encore Electric have actually announced that they're putting storage in the grid and trying it. So there's a couple of articles here from May and Dallas News. And they're starting to look at how they use storage for PV smoothing, reliability. And the chart you see there is actually doing some modeling. I mentioned modeling before I started, to actually look at PV rejection. So the more PV you get on the grid, and in the States here, as you know, we have slightly longer feeders, you start to get this phenomenon of voltage fluctuations, some pretty severe ones. So you have 2 choices. You either build a new grid, or you put storage in the grid to start negating some of those things. So they started working on that, and this is my pitch around regulatory change. So the 1980s, we saw the deregulation model that really exists today. So you have a wires company, a generation company, etc. So Encore is significant in that it's a wires company and should not, in theory, have energy storage. Yet it has the very system that at the grid edge it needs energy storage. So the policies and the regulation to allow storage to go into the grid is something that you keep hearing about. So the Encore has 2 choices: to either stop having PV added to the grid, probably not going to work for long, or it's going to have to start changing the grid itself, very expensive. So I'd encourage you to look at this particular project as it's starting to learn some of those aspects from a policy and regulation standpoint. And they're planning to have a full demonstration capability, I believe, in February next year, but we've already got units installed there. So there's a regulatory impact as well. So with that, that's the last of my particular ones of case studies around grid edge deployment.
All right. Thanks so much, Mike. Interesting stuff. All right, Tom. Tom Johnson from Itron.
All right. See if I can get this thing to work. Very good. Yes, good morning, good afternoon, depending on where you're at in the country. So I think everything old is new again when it comes to optimizing grid intelligence using a meter as a sensor. What I mean by that is traditionally there's been a lot of different ways to be able to control volt-var optimization. Either you could do it remotely, you could do it through heuristic models, you could do it through distribution management systems, or control center-based. This case study I'm presenting today is one that Duke Energy has been using, and It's in coordination or collaboration with Itron and with Alstom, Alstom's integrated distribution management system that is actually implementing this control center based volt-var optimization system. For Duke, one of the things was that they saw that an opportunity to leverage volt-var optimization by taking a look at the endpoint in the meter and saying, okay, can I actually access that meter data that I've been just using for billing purposes and actually extend that to the grid edge operational characteristics that could benefit our volt-var optimization system. So just to kind of level set us a little bit, by being able to utilize a centralized decision-based system like this, you're essentially taking everything from the substation on down to the meter and collectively pulling this back up into a closed-loop control system that allows you to lower the voltage, down to the 116, 117 range, still within the ANSI tolerance, but being able to basically do the 1% voltage reduction produces either 2% generation energy offset or 4% benefit from peak load. Some of these numbers are debatable, but essentially this is one of the benefits of doing volt-var optimization. So in terms of what Itron brought to this party, if I can get this thing to work, there we go. At Duke, they had deployed open-way meters in the blue sections, so of their territory. And this is kind of a gratuitous slide. I think you saw this from Jason as well, but certainly I need to acknowledge that these are regulated utilities that have an extensive territory, and within that extensive territory, they deployed the Itron open-way system in the blue and in the blue zones, both in North Carolina and Duke Midwest. Within those operational jurisdictions, they've also have invested in Alstom's LVM, or load and volt-var management system, which is part of their integrated distribution management. The objectives of the LVM is to really avoid customer voltage violations, minimize demand, peak shaving, as well as being able to implement conservation voltage reduction, minimize losses and improve power factor, and adjust power factor for system VAR support. They do this through controls that are deployed throughout the grid on Duke's system, mainly capacitors, LTCs, regulators, and then obviously distributed generators. You see the picture on the right there. It represents a visualization from Alstom's IDMS system, and what that shows you is both low voltage and high voltage conditions that can be alerted or alarmed within the visualization part of Alstom's IDMS. As I mentioned before, this is a closed loop system. It can also operate in an advisory mode or a study mode, and I'll show you in a minute how that kind of works. But for what Duke really was looking for was to be able to enable the LVM to select meters that would receive voltage measurements as well as brownout voltage alarms and guide or limit the CVR control moves from the IDMS system itself, leveraging the meter as a sensor. So as distribution connectivity changes, new meters would actually dynamically be selected based upon the most extreme simulated voltage drops from the IDMS distribution operations training simulator that had identified what those conditions would be so that they could do weighted outcomes prior to the deployment. As I mentioned, Duke has deployed approximately 500,000 Itron open-way meters. Again, these are two-way communicating over an RF mesh system, and it is in legacy Duke, Carolinas and Midwest. The meters are gathering ongoing electrical data that can be leveraged by the Alstom IDMS to improve performance and enhance the system benefits. And you see on the right-hand side, you take the meter at the grid edge, It is collected, the data is collected through the OpenWay system, and in this case, what's unique is on the right-hand side, you'll see there's something called a relay server. That's actually an interpreter or a translator that is part of the IDMS system that was a real benefit to Duke, because what that allowed them to do was not have to identify new patches or correct data normalization. The data normalization actually took place in that relay server before it was integrated into the IDMS. For just some background on what IDMS really is, it's not only a distribution SCADA system, but it's also a network modeling, distribution operations training simulator. It provides outage information, switching capabilities for FLISR applications, voltage optimization through LVM, and then also power quality analysis. So the project itself, the engagement was around the AMI DMS interface itself, and so these next few slides will be talking a little bit more specifically about what that looks like. But the bottom line is that the specific data that from the grid that they were looking for was really to include voltage readings as well as load data to optimize centralized volt-var decisions that are used for Duke's power flow calculations, load management, and load shedding, cold load mitigation, and DERMS applications. Another way to look at that architecture, and again, this is where you can see the relay server once again. So the meter from the edge goes through OpenWay. Doesn't have to just be an Itron system here. It can be other AMI vendors as well. This is a part of what was unique about this implementation, and why I say everything old is new again is because basically all we're doing was we were taking that existing AMI system with the investment in the DMS system and marrying those two together to come up with this operational intelligence. And the relay server was part of that bridging that brings the information back into the DMS. So what does this all mean from functionality? Power on as well as power off events are tracked. Meter ping, being able to actually have your DSCADA operations personnel or customer service personnel be able to ping individual meters or multiple groups of meters to be able to detect the severity of an outage. Taking a look at meter low and high voltage event processing, being able to visualize AMI voltage events both within the DMS, the DSCADA portion, as well as being able to utilize the voltage events within the LVM voltage optimization model. Something else that was really important to Duke was the ability to actually have the DMS provide an initiated internal voltage scan. So basically what it does is it would actually go out and select the meters, scan those dynamic bellwether endpoints, and utilize those for LVM purposes. So it was all done internally. You didn't have to have an external interface to do that. And then the meter KW, KVAR measurements that were used in power flow. Now this was really a strong interest in terms of what they do going forward, and that was with the solar DG installations or loads that are very difficult to model and give them a more accurate distribution state estimation. I think one of the key criteria is, and everyone in here probably knows, okay, I know what AMI is and I know what DMS is, but what was the measurement read considerations that took place, and what are the lessons learned? One of the things was that this was a legacy system. So the AMI and the DMS systems were both legacy. And so while you may hear these millisecond type operations, this is really all about multi-service for a meter that's already deployed in the field, and being able to actually pull back these meters either in a bellwether point or even groups of bellwether points to be able to manage volt-var really didn't require SCADA speeds. It just needed to be able to get the information back. And late average data was certainly better than late instantaneous data. So one of the considerations was, hey, we just need to be able to make sure that we can read the data on an as-needed basis, get this information back as an average, and then try to provide this within a specific time interval. For this project, one of the things was to capture that 5-minute interval and be able to request contingency reads in case there's changes. So you can see in the bottom there that you'd have a 5-minute interval in the blue box there, or the blue bar, and then the request would come in at 13:08 with a response 2 seconds later, and actually be an available data point for the DMS to provide control action. This is an example of the low voltage meter scan itself. So a brownout condition would be very similar to that low voltage condition I showed earlier. Again, the dynamic meter selection would be weighted by the type and extent of violation, measuring volts on a 5-minute average voltage with the response in 1 to 2 minutes, rejected if it was over 5. And the scale is really for initiated voltage scans in the 70 circuits, 2,100 reads per hour for Duke Carolinas, and Duke Midwest was looking at 500 circuits. Ultimately, Duke is looking to drive to the southeast circuits being 100,000 reads per hour. So I mentioned before about solar and other non-conforming loads. One of the key things that Duke wanted to make sure was that they actually could pull this back they have an example of a 100 kW solar site that the meter data can actually help them with both state estimation and distributed generation monitoring and power flow. Obviously this is a smaller scale activity, 3,000 meters by 2015 and 5,000 going to 15,000 reads per hour. So the example here is just to show you the types of meter 5-minute interval data that they're able to capture now and bring that back in for state estimation. They never had that before. So again, leveraging that meter as a sensor has benefited their solar DG program as well. In conclusion, leveraging the Itron AMI meters as a real-time source of information has provided Duke with some additional benefits from an existing legacy system, and that includes reduction in the number of line sensors that they required. They actually had a rate case that was looking at 5,000 line sensors as part of a existing rate case, and they now believe that they can leverage the meter as a sensor to reduce that capital expense. As well, enhanced performance of their LVM by inclusion of the voltage readings from these bellwether meters, and that being dynamic allows much greater flexibility, and we've heard that before. Reduction in truck rolls for customer outages by being able to enable meter pings for verification of outages, and then the reduction of prolonged out of tolerance voltage situations by being able to capture low and high voltage alerts. And then last is in terms of the distribution state estimation power flow calculations, that they now have better resolution through the meters. I guess one more as far as automated switching capabilities. And that's it.
Thanks so much, Tom. Perfect timing. All right, Vasilis.
Good morning. It's okay. Good morning from me as well. Really excited to be here as we were last year, and hopefully we'll be here at the same event next year. We are announcing too many things. We're growing fast, so really excited. So what I will be talking today, it is one of our biggest deployments that we're currently doing in Europe in the domain of engagement with E.ON, the German utility. It is one of the biggest advanced engagement pilots right now going on in Spain. And actually what we do, I'll just describe you the whole procedure, and this is actually what we will do and deploy in Canada from September 2014 into specific US utilities in eastern and western coast and Texas. We are a company actually in the domain of energy analytics and engagement. So the program is that we will deploy almost 700,000 home consumers in Spain. Initial pre-pilot, it's to 3,000 home consumers already started. Installation of additional hardware, of course, actually it's upon the utility to decide if they will install additional hardware in order to get real-time information from inside the house. Because as you may know, utility meters, they just give us 15 minutes intervals. One of the disruptions of the platform is that we can actually disaggregate data, so identify inside the home the individual appliances and map that with individual behaviors inside the house and the pricing of the utility. So in order to do actually the disaggregation, we go and we invest, actually the utility invests into additional hardware. But the point here is that we cannot actually, it's not important to install the whole community. So we are following actually the 20/80 rule. This is a Pareto rule. So we have advanced calibrating models, statistical models. So if, for instance, we want to identify 1,000 consumers, we go and install to roughly 200 only. So it's, those consumers are roughly selected by us, and we can actually calibrate and expand, project the model, so we can identify and can predict, we can understand what is going on to all the 1,000 consumers, so to the rest 800, only by looking on those 200 disaggregated data. This is of course important because investing in new hardware for utilities, it's a big red flag, so it costs money. So right now, we're also piloting and checking some additional and new ideas of getting real-time data from the hand, from the home area network. As you might know, Apple recently, they've just announced a new development kit for iPhone 8, where you can actually go and connect with specific devices inside the house and take data. Apparently, energy data will be one data set that individual vendors will actually support. So for us, it's a matter of time, in the next 1, 2, 3 years, that the utility actually will do the billing from the utility meter, but everything else, in terms of deep dive analytics, trend analysis, may be done by some other advanced data harvesting techniques inside the house. And this is actually where Google acquired Nest. Also we deploy to C&I customers as well, so it's roughly 40 commercial and industrial buildings. And as I told you, we will deploy the similar services to Canada from 2014 and US. So this is actually what the product looks like. The product and the whole platform that we have is not only a platform, it's a whole philosophy, new philosophy. And I will just explain to you after how we approach the engagement philosophy, the engagement methodology. Engagement is a huge buzzword right now for the utilities. So we have to analyze exactly what the actual engagement is for utilities right now. So we have a web app for the users, so the user can actually log in, see their energy consumption, make all the, the peer comparison, identify what is the optimal pricing package from the utility, okay, some classical things, but actually based on some relevant and recent studies, and you may know that not all the consumers they go and log in every day to see their curves. What we are actually investing a lot, it is the mobile app. So you can do everything from your mobile app, and you don't have to go and log into your web app. And the third module, it is an admin panel for the utilities, and this is one of the most important differentiations as well. We go and analyze data, drive and identify trends, and then we go back to the utility and we report every month some trends and clusters that we have identified inside the customer segments. I'll just deep dive on later on in this in order to understand what is the value of the utility by identifying, for instance, that there is a specific class of customers that are cooking every day in between 12 o'clock and 2 o'clock in the afternoon, okay? And then we go back to the utility and we can convince the utility to adopt a specific pricing schemes for those who actually cook every day in this time slot. The case study steps, the deployment steps, initially, this is from ground, from level 0. That means that we went to the utility, we educating and training their call center to go and grab customers. So initially, we go, one of our analysts sits with the utility, does a tariff analysis. We go to the translation as well. The platform is in Spanish, of course, is in English. We adapt, there is a big, large questionnaire that the customers, the home consumers should actually fill in. We're right now working on some advanced techniques, again, with gamification in order to convince the home consumers to give us data from their house. Also, we're working some disruptive techniques using QR codes, so you can actually go and scan a QR code from the fridge, so we can directly identify what kind of fridge you have in your house, and then, of course, identify and predict consumptions. The next step was customer acquisition, okay, all the terms and conditions, call center. If we have a meter installation, we can also adapt, go and hook up to the utilities MDM system, so we can go and get 15 minutes intervals data. But as I told you, the quest here is to go and install to some specific sub-segment of customers to install additional hardware to get 3 to 6 seconds intervals of data. So this is important for us because we go and identify how the individual appliances actually are operating or functioning inside the house, and we map that with individual behaviors inside plus individual pricing schedules from the utility. Profiling, load curves, and analysis. After we do that, we wait for roughly 2-3 months in order to obtain the advanced algorithms, give us some data, some results on the profiling. Of course, we do need 2-3 months because we have to have some historical data, and we need the algorithms to go and interact with the data. After that, we go and we start the actual engagement. And this is the biggest differentiation. As you will see later on, we go and we have integrated a whole learning management platform, learning management system inside our platform. So we go and we offer training to the home consumers, to the customers, to all the new definitions of the smart grid. Based on some recent studies, 60% of the Americans, they don't really know what a smart grid is, or they don't really know what is an electric vehicle. So we have identified a big problem in that. And in order to engage to the optimal way your customer has to be knowledge, has to be educated with all the new features and all the new definitions that currently are coming up from smart grid. So initially the analysis, sorry it's Spanish, but we, as I told you, we'll all have it in English as well. This is the initial questionnaire. The customer goes in, fills in every day, fills specific segments of the customer. We can identify how many devices they have, what is their HVAC, everything. And as soon as they keep filling in the questionnaire, they earn points. So we have a very strong gamification essence at the back. As soon as we do that, we go and we work with the utility about integration. We integrate the platform with their ERP and CRM system. So we go and check the utility information codes, the customer information code, what is actually the social security number and everything. So in order to identify every day if the customer is still with this utility or he changed. Then we have the user registration. All the user registration is be done by the mobile app. So, and as soon as you have a technician that is coming to your house to install an additional hardware, you have a special promo code for the utility. From the utility, you go and fill it in, and it's a matter of 5-10 minutes for us to be informed that somebody has installed additional hardware to your house, and then we have the integration with our MDM system, so we go and getting real-time information 3 to 6 seconds to our cloud. And we do that at the same time we can, as I told you, hook up with the utilities MDM system. So we have 3 to 6 seconds intervals plus the 15 minutes intervals from the utilities MDM. Profiling and engagement. As soon as we do that, as I told you, we have very advanced infographics inside the platform where the user can see their energy profile in real time, can play with alternative pricing schemes, can actually be engaged with the utility, can identify their utility billing, their home billing costs, and of course can receive prices. As you can see, the utility, we give the possibility to the utility to upload their own content inside or to give their own prices. So it's some alternative revenue models for the utilities because at the same time they can do marketing and advertising. Now, one of the most important things and biggest differentiations of the platform, as I told you, it is that we have integrated some strong engagement metrics and some, let's say, really advanced learning management system where the utility is able to upload educational material to the platform and push notifications, tips, quizzes, multiple choices, video, text about specific sections and specific subjects of sustainability. For instance, we can identify that specific home consumer, they have, let's say, an exceeding consumption for the lights, or they're cooking a lot. So the utility is able to develop an educational training material that can last for 1, 2, 3 weeks, or even a month, and push notifications to this specific home, educating the customer how they can cook actually more efficiently, or what is energy efficiency and why they should switch off the lights every night or when exiting their rooms. So the big thing here is to adapt training material and educational content to the individual behaviors inside one building or one house, and to check then that if we change the behaviors of the people inside the house, we have actual results. And of course we can measure these results because we have real-time information coming from the house. As soon as we have also appliances disaggregation, we can go down to the disaggregation level and we can check if this specific people inside the house, they have changed their cooking behaviors, or they have changed the way they're using the lights inside the house. But still, it's not a simple demand response message. It is a whole educational methodology. This is what we call subliminal learning. So by offering real-time educational training services to the user, we go at the same time and we measure some engagement metrics. For instance, we're measuring engagement in real time. How much you are engaged with your mobile app, how much you are engaged with a platform, how many page views you're doing, how many logins, how many tips have you read, how many quizzes have you solved, and what was your exact grade on these quizzes. At the same time, the user is able to see the neighbors, how they perform. Am I more knowledgeable than my neighbor? Do I know more things about my neighbor or from my neighbor? So as soon as the utility has all this information, we can actually go to the utility and report every month what is the actual real-time knowledge curve of their segment, of the customer segment. We know exactly how many people they know good things, many things about electrical vehicles. We know how many people they know or they have performed well, over 85% in the quizzes about sustainability, and how many people they have performed well on some quizzes and some educational material about recycling. So the utility goes then and manages the whole neighborhood as a volunteer community. So the aim here, from this engagement philosophy, it's totally different. We are human-centric, not utility-centric. So we go and we want to transform the utility into the next generation social university. Again, some snapshots from reports, advanced reports that we're giving to the utility every month. So it's a bidirectional service, a service from the utility to the users to increase their engagement, and a service from us to the utility to make them identify and make them understand well their data-driven communities. The time plan, we usually go and analyze things, let's say 1-2 months, and then we go and operate a demo, actually pilot for 6 months, and then go on to contract. We do that because we're very self-confident, of course, of the product, and we're very, very well self-confident that we're going to have a value from the utility. We're going to offer value to the utility, and the results are immediate. Some value propositions, okay? Of course, analyze the impact on customer satisfaction and build true customer loyalty. Nobody will actually want to leave from a utility that they keep training him or they keep educating him honestly on one of the hottest topics of the smart grid. Analyze additional revenue models. We can identify old fridges. We can identify appliances that should be or could be replaced. So as you can understand, we are driving, we're monetizing, and recreating, creating, identifying alternative revenue models from data analytics. And of course, analyze the potential impact of cost to acquire, cost to serve, and cost to retain. All those metrics, we're going to have some real numbers after September, October from the case study. We have already published one good case study about our methodology and GTM research, and we're going to have more numbers from this case study as well. Improve position as a clean electricity supplier, and of course, build a customer human-centric approach for engagement. But the most important thing is that we transform a utility to a social university. We transform a utility to an entity that is really cared about their customers, and they want them to educate them, and at the same time, they can measure this engagement by data-driven methodologies. Thank you so much.
Well, thanks guys for staying on time. I appreciate that. So we've got about 10-15 minutes before lunch, so if we have questions, you can ask them of the entire panel, and they can take a shot at it, or if you have specific questions for any of these gentlemen, I'm sure they'd be happy to answer them. Start up there.
Thank you. I'm Rich Morley with Eckergy Energy. Bastos, a question for you. With all the information and the change, it seems to me to be a very short step from education to punitive, where the utility can actually, once you aggregate, then disaggregate, that a utility could go back and then actually apply punitive rating structures to a given person. What are you doing to protect the individual from punitive aspects on pricing?
Can you elaborate? You mean like a privacy issues on the
well,
data?
Not only privacy. I mean, you've said basically you can aggregate the data, you can look at it, then you can disaggregate it back to an individual. what would then stop the utility from saying, okay, you're cooking at 12:30 and I don't want you to cook at 12:30, so I'm going to hit you with a rate penalty if you cook at 12:30. Right now it looks very favorable. Everything's being done positively to the consumer, but remember Germany many years ago, not the Germany of today, but the Germany of our forefathers. It just seems a little bit too much Big Brother with the risk of reaching out and being punitive. How do you comment to that?
Well, yeah, there is a big issue right now in privacy in general, but what we're trying to do is to take the best of value out of those disaggregated data. So, of course, the utility won't push someone to cook later on because they may have children that may go to school, or they're working alternative hours, so they have to eat, of course, in between 12 and 2 o'clock in the morning. That's certain. What we're trying to do is just to trying to push and change behaviors from, let's say, people that are much more elastic to do that. So nobody will push you actually to do something, but certainly the utility will propose you to do something. So it's up to you, the option, it's up to you to decide whatever you want to do, but no utilities actually will push you doing something, or no utility will actually give you a penalty on the okay, if it's a critical peak pricing, it's a penalty through the pricing module, through the pricing strategy, but no utility actually will go and push you to do something or to change your internal behavior, but will propose you to do things. And by proposing things, it's not only proposing that you should do that because of that and that, they will actually educate you around that. Yeah, this is financial incentives. If you're rich, you don't care. So you're using social incentives. Sorry? Yeah, I mean, financial incentives is good, they're good, but many financial-based demand response programs, they fail because if you're rich, you're inelastic to change your behavior because you just pay more. So social incentives, it's an alternative solution to that. You're welcome.
All right, another question? People are ready for lunch. All right. Well, I'm sure these gentlemen will, be around on near the stage. If anyone is too shy, come on up, and I'm sure they'd be happy to chat with you. I'd like to thank all of you. Thank you very much. Great information. Oh, one quick note. If, like I said,